Here's an example of a question that's going to focus on hypothesis testing looking at proportions. So when we're thinking of proportion, we're thinking of a random variable that can take on the value of 1 or 0. And we're going to ask several people this question. In this example, the question is, are you unemployed? So that random variable can take on a 1 if yes and 0 if no. And so we're looking at both France and the US. So in France, there were 1,000 people that were asked the question, are you unemployed? And 109 of them answered yes. So that means our p hat is 109 over 1,000. And the same thing for the US. What this tells us then is that our random variable x is going to be distributed as a Bernoulli distribution with parameter p, where that's the proportion or the number of people answering yes. So we can come up with a measure of p hat. This is equal to the number of people who say yes divided by the number of individuals in the survey. So right here we get p hat is equal to 0.109 for France. But we could also look at then the expected value of p hat, and if I work through this, we'll find that the expected value is p. I can also take the variance of p hat, and if I work through that, that will equal p, 1 minus p over n. So with this information, we can then employ the central limit theorem, which says that it doesn't matter where the underlying distribution is, that x bar will be distributed normally as the sample size gets big with the expected value of p hat, which is p, and the variance of p hat, which is p, 1 minus p over n. And so that's what we have for the central limit theorem. The other thing to note here is another way to write x bar is simply p hat. So now that we have the central limit theorem that says that, we can then normalize this to say that p hat minus p over the variance, which is p 1 minus p over n, is going to be distributed as a standard normal. So we can use this and then turn to our standard normal distribution table to be able to answer these questions. So that's the foundation of what we have as we go to answer questions 1 through 4. So using this information, let's go ahead and calculate a 95% confidence interval for both France and the US. So in these examples, what we're going to ask, so here is France. What we want to know is what's the probability that, and we can look up in our table of the 95% confidence interval. So 1.96 is going to be between p hat minus p over p 1 minus p over n is 1.96. And we want this to be 0.95. So this is the setup that we have. And now what we're trying to find is we know p hat, we know p 1 minus p, so we just need to then calculate from here. So we can change this for France, that the confidence interval at the 95% is equal to p hat, which is 109 over 1,000, plus or minus our z-score, 1.96, times the square root of p minus 1 minus p, which is 0.109 times 1 minus 0.109 all over 1,000. And so this will set up our confidence interval for France as the true population mean will be between 0.090 and 0.128. So from this survey, we can estimate and be 95% certain that the true population unemployment rate is between 9% and 12.8%. We can do that same setup for the US. And we can just write this as the US is going to have their number, which is going to be whoops, here we go, sorry. 38 over 500 plus or minus 1.96 times the square root of 0.076, 1 minus 0.076, all over 500. And that means the U.S. unemployment rate, we are 95% certain that it is between 5.3% and 9.9%. And that's how we can answer part A, or the part 1 of this question. Now let's look at part 2. Create a 95% confidence interval of the population difference between the unemployment rate in France and the US. So here we're going to ask something slightly different. What we're looking for is P hat of France minus P hat of the US. That's our new X bar. So we can set up our confidence interval of 95% is going to equal this X bar plus or minus 1.96 times, we're going to have P hat F, 1 minus P hat F, over the number of F, plus P hat US, 1 minus P hat US, over the number of the US. And the reason we can do this part right here is because we can assume that that the sample in the US is independent from France, and therefore there is no covariance term between them. And we're also using the estimated variance right here, and we can do that with the central limit theorem that says it's going to be distributed normally. So now with this, I can go ahead and put in the numbers. This is equal to, we can look at the numbers for France, which is 0.109 minus the numbers for the US, 0.076, plus or minus 1.96. And now it's going to get a little nasty, but we can do it. 0.109, 1 minus 0.109 over 1,000 plus 0.076 times 1 minus 0.076 over 500, and that's for the US. So I'd get out my calculator and I'd calculate this, and I'd find that the difference in the unemployment rate is between 0.003 at the lower end or 0.063. So I'm 95% certain that the true difference in unemployment rate in the population between these two countries is between 0.3% and 6.3%. Now let's go to question 3. Let's find a p-value of a one-sided test where PF minus PUS is greater than 2. So we're asking can we create a confidence interval of the difference between the unemployment rate of France and US is greater than 2 percentage points. So let's go ahead and do that right here. So we can set this up as our test statistic is going to equal, and here we have, let's start with our null hypothesis. Let's move our test statistic down there. Our null hypothesis is that PF minus PUS is equal to 0.02. Our alternative hypothesis is that PF minus PUS is greater than 0.02. So now we would calculate our test statistic here, where we would look at PF hat minus PUS hat. So that's our sample, minus our population, which in this case is going to be 0.02, divided by the square root of PF hat 1 minus PF hat over NF plus P hat US 1 minus P hat US over N US. So a pretty gnarly number, and we can plug in what we have for that. So P hat of France we had was 0.109. P hat for the US is 0.076. NF is 1,000 for France and 500 for the US. So we keep plugging all those numbers in, and what we get here is equal to 0.84. And so if I draw this on the graph, we have calculated our test statistic, in this case our z-score, as 0.84. And so the p-value, because I'm looking at a one-tailed test, is I'm going to look at what is the area to the right of this curve. So I'm going to look up in my table A, I'm going to look up 0.84 on the outside to find what's the probability to the right of the inside. And what I would find is that the p-value is equal to 0.2005. And so that's the p-value to the right there. Now let's go to the last one. Question 4. What if our null hypothesis is that the unemployment rates are equal? So let's go ahead and write this null hypothesis. Let's grab a new page for this one. So our null hypothesis is that the P in France is equal to the unemployment rate in the US, the proportion. The alternative hypothesis is that they are not equal. So let's consider what this means. What this means here is that the proportion of France is equal to the proportion of the US, and I can shorthand that with just calling that the proportion. And so let's go ahead and set up our test statistic. Our test statistic is equal to, this is what we had similar to before, P hat F minus P hat US minus PF minus PUS. Okay, so here's X bar minus mu. Okay, it should be similar to that. Divided by the square root P hat F, 1 minus P hat F over NF plus P hat US, 1 minus P hat US over N US. But now here is, because I've imposed that by my assumption PF equals PUS equals P, I can simplify this to write this as P hat F minus P hat US minus PF minus PUS over, and now I can factor out a P1 minus P times 1 over NF plus 1 over NUS. And that's because of this here. I can simplify that and then factor out P1 minus P here and P and 1 minus P there. Well, now we can calculate our P. So our null hypothesis is that we have two binomial random variables with equal P but different N. Therefore, we can write P is equal to the number of yeses in France plus the number of yeses in the US over the total number in both countries. And that means our P is 0.0908. Is if we impose that the P is the same between them, then this is what we would get. Now we can then go back to our test statistic. T-stat is equal to 0.109 minus 0.076 minus 0. This is from our null hypothesis saying that they're the same. divided by the square root of 0.0908, 1 minus 0.0908 times 1 over 1,000 plus 1 over 500. And I can calculate this, and that would be 2.10. Now I can look at my graph to see what that would look like. So this is my normal distribution. I've calculated my z-score, let's write that in blue, as 2.10. Now if I'm looking at a alpha of 95%, so if alpha equals 0.05, well then I do a two-tailed test here, where this would be 1.96, this would be negative 1.96. Therefore, this critical value falls within the range of the rejection region. So therefore, I would reject the null. That unemployment is the same in France as the US. And that's how I can calculate it from there. The other thing I can do is I can actually look at the p-value. So here, the area to the right of this 2.10 is 0.0179, but I also need to consider the area if I'm at negative 2.10, which is also 0.0179. So in this case, my p-value is equal to 2 times 0.0179, which is equal to 0.0358. And notice that this is less than alpha, 0.05, and so I would still reject the null hypothesis. And that's how we can answer these 4 questions of doing hypothesis testing with proportions.